Alrighty, in this video we are going to look at some trig derivatives. We're going to focus today on sine, cosine, and tangent. I want to walk you through a graphical argument for the derivatives of sine and cosine, and then using our knowledge that we acquire graphically, we will come up with a derivative for tangent as well. That's what's going to happen. So we're going to start here with sine of x, and we are going to try to determine what y prime is graphically. So what I'm going to do is use the arguments that we've talked about to try to construct a graph of the derivative of sine, beginning with these locations where I have horizontal tangent lines. Horizontal tangent lines on my graph of y will correspond to x-intercepts on my graph of y prime. So everywhere that I have either a relative maximum or a relative minimum on my derivative graph, those will become x-intercepts. And then if I focus on this portion, and this portion, and this portion, what I can determine about those points is that is where the slopes are the steepest. That is where the slopes are the most extreme. So if we direct our attention to the center here, this slope from this point to this point, this is where it's the steepest, and we're going to say that is a slope of 1. We're not just making that up, it actually is true that is a slope of 1. And in the same way, the slope at pi would be the same, only be negative, so negative 1. And then again at, I should say 2 pi. At 2 pi, we're back up here at positive 1. And what's neat about this graph is that it's cyclical, it's periodic, so it repeats itself. If we connect these dots, we're going to see this function. And it just so happens, this is no coincidence, it just so happens that this blue curve that I have sketched is the exact same as y equals sine of x. It's shifted pi over 2 units to the left. And that is the graph of cosine. So this is our first aha moment. The derivative of sine is cosine. We need to know that, and I've just walked you through a quick graphical argument for why that is. There is an analytic approach as well. We could do the limit definition of a derivative and use some properties, some trig properties, and determine this exact same thing, that the derivative of sine is equal to cosine. Let's go ahead and do the exact same game for the cosine. If my y function is cosine of x, we want to determine what y prime is, and we're going to play the exact same game. We're going to use the exact same argument, starting with these points where I have horizontal tangent lines. I'm going to plot those along my x-axis as my x-intercept, because I am communicating that the derivative at those points is 0. And again, we have got steep slopes in the center here of 1 and negative 1, alternating between 1 and negative 1. So I'm just going to connect these dots up, and let's look at what we've got. So if it's true that really the sine and the cosine curve are the same curve, they're just shifted versions of each other, or translated versions of each other. The derivative of cosine, a good guess would be to say that it is sine, but it's actually not sine, and you can see that here on this red graph. Sine starts at 0, 0, and starts by going up, which is not the case. This is going down. So it just so happens that this is the sine graph flipped upside down, or in other words, it's negative sine of x. The derivative of cosine is negative sine of x. So to summarize what we just saw, if f of x is sine of x, the derivative is cosine. And if f of x is cosine, the derivative is negative sine. So using this, we are going to determine the derivative of tangent of x as well. But before I do that, let me just say a quick word about what would happen if I wanted to find the derivative of negative sine of x. This is the same as negative 1 times the sine of x. And we can think of this as the product rule. We could do the product rule and take the first times the derivative of the second plus the second times the derivative of the first. The derivative of -1 is 0, so this whole term goes to 0, leaving us with negative cosine of x. So our negative stays. The negative stays. When we have the derivative of negative sine of x, we get negative cosine of x. And in the same way, if I want to find the derivative of negative cosine of x, f prime of x would equal, there's my negative, and then the derivative of cosine is negative sine of x. So negative sine of x is simply sine of x. So let's go ahead and tackle the derivative of tangent of x. This one gets a little bit weird, and the way that we're going to do this is by rewriting tangent as sine of x divided by cosine of x, and finding the derivative of this by recognizing that sine over cosine is a quotient. It's a fraction, so we're going to use the quotient rule and sing our song. Low d high less high d low, draw the line down below, denominator squared must go. So here we go. Low d high, the derivative of sine is cosine. Low d high less high d low, the derivative of cosine is negative sine. Draw the line, and down below, the denominator squared must go. A quick note about this, when you square cosine, it's standard practice to put the 2 in between the cosine and the x, because otherwise it could be confusing. You may think that you are just squaring the x. So what you should know, though, to be reminded of, is that this is the same thing as cosine of x squared. Those are equivalent. So let's go ahead and continue with this. Cosine times cosine is cosine squared. And then we are going to be subtracting a negative value. I'm going to be adding sine squared. And this whole thing is divided by cosine squared. And we can take this a step farther because we remember our super handy Pythagorean identities that remind us that the cosine squared plus sine squared is equal to 1. So this is where I'm at, and remember that this property that tells us that this equals to 1, that this equals 1, all that is the Pythagorean theorem. If you remember that the cosine, we think of that as our x direction, sine we think of as our y direction, and within the context of our unit circle, the radius is always 1, so we have x squared plus y squared is equal to 1 squared, which is equal to 1. So here we go, 1 over cosine squared. We're not going to leave it like that, though. We never are going to, well, it's not that we never will see that, but typically you won't see the derivative of tangent expressed as 1 over cosine squared. Remember that 1 over cosine, by definition, is secant. Secant is defined as the reciprocal of cosine. So if I have 1 over cosine times 1 over cosine, I have secant squared. The derivative of tangent of x is secant squared. So we'll add that to our 3 derivatives now that we are responsible for sine, cosine, and tangent.